Hello. So in this slideshow, I'm going to demonstrate how P versus NP is undecidable. And this is a problem that can be reduced from a very simple problem where you try to compare two things that are both similar and different at the same time, and you find that there's no way to do a proper comparison without running into contradictions. So to get things clear, if it's a concern, so I have a bachelor's in computer science. I will admit that I have failed a course on automata theory, but I have improved on it though. So let's consider a problem. So you have a collection of objects, and they are different from each other. Now, if you were to consider the collection a space, you can easily argue that these objects are the same, since they occupy the same space, which is they are in the collection. And so here's the question. Are the objects similar and different to each other? Now, the answer to this question is very difficult to answer, and you'd be right to have this predicament where you find that it's just contradiction, because you can't have two things at the same time. And so this problem I will call the comparison problem. From when I say paradox, I refer to this dilemma that the comparison problem tries to tackle, which is having two things be tautologically equivalent. In other words, they're both you having your cake and eat it, for example. So I like to propose a theorem called the Theorem of Paradoxy. There is no consistent algorithm when you have two things or more, or any that have both a similarities and a differences. So it just really doesn't make sense to try to even do something like that, because you wind up with contradictions or other inconsistencies if in that matter. We may think that it makes sense to avoid it, and we would implicitly not run into this paradox, but we do anyway. And the worst part is that we try to come up with an answer for something that may not be correct. It's if anything, there's plenty some things we want to compare are passionate, and it comes down to is logic. If we consider logic of things, we find that even logic has its limitations. And so it is why I say the solution to the comparison problem is undecidable, at least in its pure abstract form. So let's consider a proof. A and B are sets. They are proper subsets of this universal set. Let's make this agreement that if A were to be the same as the union of A and B, and that equals B, then it stands that they are a proper subset. Let's define a set where it's the intersection of A and B. Now let's consider two lemmas. If A doesn't equal B, this is true if and only if C is a null set. On the other hand, if A and B are the same, this would be true if and only if A is equal to the union of A and B, which also is equal to B. And so let's take the complement of the first lemma. We find that that C can't be a null set if and only if A is B, which by the second lemma means that A is a union of B, which thus would imply that C must be the same size as B. It would, and as well as A, because A and B are the same, right? If we were to take the last step and complement it, we find that C is a null set if and only if the complement of A and the complement of B intersected to yield some sort of set. If we are to continue with the first lemma, A and B are the same if and only if the complement of A intersecting with the complement of B gives us what? And whatever that is, we don't know because it wasn't even defined at all. And thus I conclude that in the pure abstract form, I can't really express this paradox without running into this inconsistency. In this next proof, I'm going to show that the comparison problem is undecidable. Now, what I will do is that I will make a reduction from the halting problem. Now, I will not be using the discrete math as shown before, but instead the pseudocode version of the halting problem. Now, usually, if it is found that if you were to feed the halting algorithm itself and you complemented that output and it says that it didn't halt, then it would have halted considering that the complement is true. Otherwise, if the algorithm did halt, the complement is false and it loops. And this is pretty much the basic form of how the halting problem is shown to be undecidable. And this is the approach I will be using as I'm making my reduction. So what I will do is that I'm going to make two functions. So the first function takes the two sets that I have mentioned earlier in my proof and have it return true if A and B are the same. And for my other function, if they are different, if it happens that the intersection of A and B is a null set, then it would return true. Now, if I were to arrange it where if either one were true, it would go into a loop. Otherwise, if it's both or neither, then it would return true. Now, as you notice, is that it would be quite hard to be able to see if this algorithm would halt. Because, obviously, if A and B were happen to be different or similar, then it would go into a loop. Otherwise, it just returns true. And thus, you have a situation where it isn't quite clear whether or not this algorithm will halt or not. It might return true, or it will just go forever. And thus, the comparison problem is undecidable. Now that I have discussed the theorem and demonstrated a problem called the comparison problem being undecidable, I think we're ready to show how the P versus NP problem is also undecidable. In that problem set, you have these hierarchies of problems that go up in complexity, or to put it simply, they get harder. So P is this particular set in which it's the problems that can be solved polynomially or a reasonable amount of time, as well as checked polynomially. The problems that could be checked polynomially but solved exponentially, or at least solved with polynomially with a non-deterministic algorithm, is NP. Now, I will not get into NP hard, but I will focus on P and NP only. The problem with P versus NP is the comparison aspect of it. So if you had the solution, the solution could be which is a certificate, and you can find ways to make a certificate that is 100% correct every time from this best method you can do. Then it can be argued that it's the same as solving it. This is what I think when someone asks me if checking is the same as solving. So you could, right? And it does 100%, and it does good 100% of the time, right? You find that like methods to making better certificates only solves the unique problem, despite that problem being in the same set as all the other problems. And the reason I say this is because like, if you were to be realistic, you find that there are so many varieties of traveling salesman problems out there, both easy and hard. So, just because there are some easy traveling salesman problems doesn't mean the easy problem is the same as the hard problem. And if you think about my paradox, that sort of method of doing two things at the same time, it's undecidable. Now let's consider the following. It appears that determinism is a more rigorous aspect in computation theory, at least in automata theory. Non-determinism is not well defined. What the non-deterministic algorithm likely does is that it picks a path that will be likely to lead to a solution. And if that likelihood was increased, then you have a algorithm that makes a good guess 100% of the time, that it might as well be like deterministically knowing the solution. And so from what I can gather about this idea of taking an algorithm in P and transforming it to NP, that same algorithm should allow you to solve the problem in polynomial time as well, since, well, that algorithm was in P. If you try to transform an algorithm that is from P into NP, that algorithm winds up being in EXP. So if you were to, say, find this non-deterministic algorithm that happens to exist somehow, then it's possible that, like, you can just make a conversion to that P algorithm, and that one P algorithm could then be used to solve all the problems in NP, as if it were doing it as if it somehow reduces the complexity of the problem to begin with. So now here's what I'm going to do to prove P versus NP is undecidable. We know that P is a proper subset of NP when we consider that that these are problems solvable in polynomial time regardless of the algorithm. If we were to make this proposal, if we find that the intersection between the two is some sort of set R, it should imply that R could be in the space of exponential algorithms, or it's just a null set. R is null when the polynomial timing is considered, which is what I have right here. This is why P is a proper subset of NP, on the basis of it being polynomial. If we just stick to determinism, then we find that R would be a proper subset of EXP. If you were to just take the complement of this if statement, so far this statement is consistent. R has to be some sort of set, and it can't be empty at all. And R cannot be an EXP, so it should be harder than EXP. Now let's consider two lemmas. If P didn't equal NP, then R would be a null set, which implies that P and NP are different. If P and NP are the same, then P must be equal to the union of P and NP, which is also equal to NP, and thus implies the similarities. All of this is true, and everything seems consistent. Now, if I were to apply the theorem of paradoxy, we find that P versus NP is undecidable. We find that because differences and similarities do exist, and are justified so from the previous rules we have established, then it should hold that P versus NP must be undecidable. So, but just because we can guess the problem easily does not imply that we can also know the problem as well. Consider predicting the future. there are some things we can predict and some things we cannot. There are some things that were meant to go in one direction, but turns out not to be the case. Even with possible methods, you can never truly predict the future. And this would make sense, because if that were the case, then, like, we don't need meteorologists, we don't need, we could just live independent lives, we wouldn't need a government at all, we could just know what to do, and life would be easy from there. And this wouldn't make any sense either, because if you know there's some methods to predicting the future, such as population growth, maybe not the behavior of the population, but you can predict its growth. Can you truly predict the future? I don't know. Sorry, David Hilbert, but we can't know everything.